Hi Wildcats, this is an overview of Unit 7 Focus Question 1. So in this focus question, we're going to be looking at how we are describing an object's motion when it's moving in two dimensions. But before we can get there, we really need to get good at drawing vectors. So we've worked with vectors before, we know they have magnitude and direction, but we need to make sure we're good at drawing them, especially when they're in two dimensions. So here, I've got a little picture, right? So here is a student and it tells us they walk 9 blocks east. So their displacement is 9 blocks to the right or east. So here's the arrow or vector that represents the magnitude and direction of their displacement. And then because it's real life, they don't just walk in one direction, they turn and they walk 5 blocks north. So where is their final position? Well, their final position is up here in that spot, and they started here, and their displacement is the direct line vector between those 2 points. So it won't be very straight, but this is their resultant vector, that black line. And so now the tricky part is like it's in X and Y, right? And so we need some way to describe this. And if you look at this, you'll realize that this is a triangle. And so that's going to help us. It also falls right in here. Like this is our vector, somewhere between north and east. And so what we'll see is we're going to end up using angles to begin to describe our vectors when they're in two dimensions, because just north or east positive and west-south negative is no longer going to work, because quickly we'll run into a situation where, like this purple line, what if our resultant vector was down here? East is positive, but south is negative. Something can't be positive, negative. And so this system doesn't really work in two dimensions. And so we need to use these cardinal directions. So let's get into how to do that. We recently talked about that. I just want to bring one more term back, and that is the resultant vector. So the resultant vector is the vector that is the sum or total of two or more component vectors. So components are the parts of that make up the resultant. So in this picture here, vector A, so from home to your friend's house, is the first component, and then from your friend's house to school is, let's see, these are displacement. This is the second component, and the resultant of those two components is this red line, which is also a vector, because this is your initial position and this is your final position. And displacement is change in position, magnitude, and direction. So C here is the resultant of A and B. Okay, so components, resultants, let's get into this. Here is our scenario. So we have a student that walks 8 meters south. So we'll draw that. Again, I'm just going to represent what it is. So here is their first vector. So this is 8 meters to the south. And then they turn and east and walk 4 meters. So if it helps you, north, south, west, east. So then they walk 4 meters. Okay, now I need to be approximate. This vector should be about the same as, or excuse me, about half of what this one is. Because if this is 8 south, 4 east should be about half that. And so my resultant would be approximately that. Okay, so now how big is that? I don't know. What direction is it? It can't be positive because it's also south. And so we need directions. Okay, and so that's how we're going to start to do this. This is southeast, so we can't use positive or negative. And so now when we get vectors that are in two dimensions, we express them as an angle of rotation from east, north, south, or west. So there's two ways I could describe this resultant vector. This black line and this green line are supposed to represent the same thing. 8 meters south, 4 meters east. And so if I got out a protractor and measured, I could say there's two ways to describe this angle. Remember complementary angles from math class, right? So this angle is 30 degrees. And so how far have I gone? Well, if I were facing south to get to this arrow, I would have to go 30 degrees east of south. So we could say that this, whatever this is, this number is, this vector is 30 degrees east of south. Another way to do this is, instead of facing south, I could face east, and then I could go south of east. Well, how far south of east would I have to go? I would have to go 60 degrees south of east. And so I would get this angle. These two mean the same thing. Either of these get us to the same spot. When in doubt, I highly recommend just picturing yourself, right? How do I get to this angle? Well, if I'm facing south, I would have to turn east of south. How far? 30 degrees. If I'm facing east, I would have to go south, turn myself south of east to get to this point. How far? 60 degrees. Okay, so the big idea here is that 2D vectors can't be described accurately using positive or negative like we did with 1D vectors, and so we need to use specific angles and directions. So let's practice that. Okay, so here's how I kind of did this. But here are the steps if you want these for your notes, or if you just want to think through these. So first thing we need to do is determine a reasonable scale. So I haven't done that yet, but it's impossible for me to draw like an 8-meter line on a sheet of paper. It's too big. So I need to use a scale. So I might say 1 centimeter is equal to 1 meter, or right, vectors could be speed or velocity, so meters per second. So I could say every 1 centimeter represents 1 meter per second that an object has in terms of its velocity. And once I have a scale, I'm going to draw a dot to represent that vector. And then we're going to call that the tail of the vector. You'll see why we need names for them. We'll get the approximate angle of it. So I guess I can just run through this. So here is my, I will just say our scale is 1 centimeter per meter per second. So here is my tail. Right here, here's my dot. Sometimes it's helpful for me to give myself like a little compass that I'm starting from. Okay, so here's my dot, the tail of my vector. Let's say it's 30 degrees north of east. Okay, so here is east. So, right, this is east. So I need to go this direction, north of east. How far? 30 degrees. Well, I don't have a protractor here, so I'm just going to approximate. We'll say that that is 30 degrees. This angle right here is 30. Okay, and I would draw my line however long. Let's say it goes out to here. And then I would end it with an arrow, and that is the tip. Okay, so my vector has a tip, that's the arrow where I end, and a tail, and that's where I start. So tip and tail. And this would be the vector that represented, I don't know, some magnitude at 30 degrees north of east. Okay, so I figured we could walk through a couple of these. Here is the first one that I have. I have the steps over here in case it helps to see them as we walk through this. So in this case, a student walks 20 meters at 25 degrees north of east. Okay, so if I have a ruler, I can grab that, take this out here. I don't even care about the angle, so we'll just do this. Especially, I don't expect you to have protractors at home since we're not doing these in class. So here is the tail of my vector right there. 20 meters, 25 degrees west of north. Okay, so I'll show you, I can approximate without even the ruler. We'll just say 1 centimeter is equal to, let's say 5 meters. Because if I did 1 centimeter is 1 meter, I'd have to draw a 25 centimeter line on my paper, and that's going to be long. So 1 centimeter is 5 meters. So therefore my line is going to be 4 centimeters long, 25 degrees west of north. Okay, so this is north right here. There's north, and I want to go west of north, so I'm going to go that way. And then 25 degrees. Well, let's see, if that's 45, 25, I'll do this in blue. 25 is going to be, if this is 45, 25's here. So we'll say it's there. And I'm not taking a ruler to it, but we'll assume this is 4 centimeters. Okay, so, and then I would label this. Here is my angle. That angle is 25 degrees west of north. And this vector is 20 meters. So I would say this vector, this line represents a object walking or student walking 20 meters at 25 degrees west of north. Okay, we can do this 5 meters per second. We'll do this in a different color. Set up our little compass again right here. Okay, so 5 meters per second, we'll say 1 centimeter is equal to 1 meter per second, right? Because I can draw a line 5 centimeters. 15 degrees south of east. Okay, so here's east, here's south, so I want to go that way. 15 degrees, again, here's 45, so 15's maybe right here. Okay, tail, and I want a 5 centimeter line now because I'm going 5 meters per second, so let's go like here, about. And I get my ruler out and actually measure if I were doing this at home. Again, I'm just approximating, okay? You don't have to be super accurate. We want to approximate. Last one, do this. Okay, you might want to pause, see if you can do this one. I'll do different color. So this one is above the horizontal. So here's the horizontal. It does not tell us if they're going 20 degrees above, if they're going east or west. I'll assume this is velocity, so that means this is positive. So I'm going over here. So above the horizontal, so I'll say this is horizontal 20 degrees, let's say here. I'll stick with that same key. So this would be my vector, where this is 20 degrees. Okay, so hopefully that helps. Jumping back, now that we can draw a vector, we need to be able to figure out resultants. So again, I won't run through all of these steps. Just reading them to you, we'll use them in a second here, but you can pause this if you want these for your notes. In short, we're going to draw our two components, then draw the resultant between them, and then estimate. So let's go do that. Okay, so here is a problem that I have. A student walks 8 meters south. Okay, so this is going to have more than one. So here is my tail, my first vector, right? 8 meters south, so 8 south, we'll say 8 centimeters, about like that. And then they turn east and walk 4 meters. Oh, we just did this one. Okay, oh wait, there's more. So here's 4, so that's about like that. Okay, it says, and then they turn north and walk 2 meters. Oh boy, okay, so a fourth of that. So like here. So here is my tail, tip. We always draw vectors tip to tail. So tip to tail, or excuse me, the tip of this one is touching the tail of this one. The tip of this one is touching the tail of this one. So I just start, right? I connect them. And so my resultant, I draw from tail to, I'm going to miss it. Oh, that was close. Tip. Okay, so I picked a reasonable scale. I said about like 1 centimeter is equal to 1 meter. Draw my first vector, appropriate magnitude and size. Second, keep going. Third, tip to tail always. And then when I'm done, I start my resultant vector at the where I started, so the tail of the very first vector, and I end it at the tip of the very last vector. Okay, so this is my resultant. Now, we got to estimate what this is. So if I said this is 8, okay, this is where I'm going to actually have to use my ruler here, and you would too as well. Oops. Okay, so if you're, this is, I said in class, it's going to be helpful to have a ruler here. Come on. There we go. Okay, now zoom in. Okay, so if this is 8, 1, 2, 3, 4, 5, 6, 7. Well, we can count dots too, I suppose, huh? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We'll just say it's about 18 to make my life easy. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if 18 is about 8, then 11 is going to be, we'll just say 6. Again, estimating, right? Okay, so we would say that this resultant, it's probably a little less than 6, is 6 meters at, and then now I got to pick my angle, right? So now I got to estimate here. So what direction are we going? I'm going to go this way, so east. So I'm going south of east. Okay, so it's going to be some degree south of east. Okay, how far do I have to go? Well, honestly, that looks like 45 degrees to me. So 45 degrees south of east. Now, if we were in class and they give you all protractors, you could measure it, but we're just going to need to approximate. So this is 6 meters at 45 degrees south of east. So when it says what is their displacement, this student Even though they went this way, then this way, then this way, their overall displacement is 6 meters at 45 degrees south of east. Okay, just for the sake of practice, let's say I estimated this to actually be 50. Okay, so I estimated that to be 50 degrees south of east. I could do this another way. You don't have to go east. You could start by thinking about this from south. So then you're going east of south. So I could also say this is 6 meters at, now this is less, 40 degrees east of south. These are complementary angles, right? They add up to 90. So if I had a protractor and measured this to be 50, I could also have measured this to be 40. It's the same angle. Okay, finishing up here. We did that problem. There are some properties that vectors have that are useful to know. So the first is that vectors can be moved parallel to themselves in a diagram. So I want to go back to this one for a second. Oops, what I did here. Another way for me to have done this is to move this vector here and then move this vector here, and guess what? Oh my gosh, I end up at the same spot. So notice what I'm doing. I am moving these vectors, however, I am moving them parallel to where they would be drawn, or where they're originally drawn. I can't like take this guy and rotate it 90 degrees. I'm changing it then. But I can move it, and then these add together, right? Because this is negative 8, and then plus 2, so 6. And then I can move this here. It doesn't change any property about it. It's basically just changing the order in which I put them together, which is therefore the next one. Vectors can be added in any order. It does not matter if you go vector 1, then 2, then 3, or add vector 1, then 3, then 2, you're going to get the same answer. And that's what we have here. So you're showing, they've drawn this, right? The student walks north, then east, then north, then west, then north. They've done this a different way. The student walks east, then north, then west, then north, then north. You get the same resultant vector. Same thing here where I'm moving these vectors. 6, then 2. Doesn't matter if I go 6, then 2 north, then 6 east. These lines are exactly the same resultant. Okay? The other thing that we need to be aware of is that you can never subtract a vector. Like, doesn't make any sense. Because negative doesn't mean to take away in physics, it's direction. So it doesn't make any sense to go 10 minus 4. What we're really doing when we have a negative direction is we are saying 10 meters, and it's east, so that's plus 10 meters, and then plus, and I'm just doing the red, plus 4 meters, and since it's west, it's negative. Okay, so this is what I mean by when I say I'm adding the opposite direction. I'm not doing 10 minus 4. I understand math is going to give me the same answer here, but it's an important concept to understand that we aren't taking away, we're just adding to the overall distance, because while the resultant in its displacement would be 6 meters here, the distance, if I were measuring distance here, this student walked 14 meters, and this student, according to this, only walked 6, because somehow they walked 10 and then unwalked 4. That does not make any sense in the real world. Okay, so you kind of have to unmath. I know in math, negative means one thing. In physics, we use it very different. Okay, so I've got one more problem to just kind of work through some of those properties down here. We'll just get rid of our ruler. Hey, a student drives a car 20 meters per second west. So I'm going to say, let's see, the biggest number I have is 30. So let's say 1 centimeter is approximately, I'm being very approximate here, 1 centimeter is approximately 5 meters per second. Okay, so my very first line, here's where I start, here's my little compass. Okay, so 20 meters per second west. So I would need 1, 2, 3, 4. So we'll call that 4. So that's 20 meters. Then they turn and drive 30 meters per second north. So that would be 6, right? 30 meters per second. Oh no, at 30 degrees north. Okay, so here we go. Now 30 degrees north of west is what this must mean. Okay, so here is west, so I'm going north 30 degrees from west. So let's see my 30 degrees, I'll call it right here, and it's 30 meters per second, so it should be a little longer. Okay, so there's that. This is 30 degrees. and then they turn and drive 10 meters per second south. Okay, 30 meters per second. Oh, so 10 meters per second south. So we'll go from here, right, tip to tail. I'm just doing these tip to tail, 10. So that's like here. Okay, and then before turning again and travels with a velocity of 10 meters per second west. Okay, so we're going west again. This one was 10. I need a new color. Oh, we'll go rainbow. Okay, velocity of 10 meters per second west. So same thing, tip to tail. Okay, 10. So like there. Okay, so look, this is a big jumbled mess, and if I try to draw this line between these, that's going to be like a disaster. So I'm going to make my life easy, okay? I can move this guy here, and then I can move this guy here. Tip to tail, right? Doesn't matter as long as I don't rotate them, but I'm doing them tip to tail, right? Tip to tail, tip to tail. I can move them as long as they stay parallel to where they originally started, and I always go tip to tail. Okay, actually, I wonder, let's do this. Let's go back to where I had them. So I'm going to draw this as a red line. So this is the order they came in, right? This is going to be terrible. I need a ruler, and my dog's barking. Okay, so this is where I start. That's where I finish, right there. So I need to align those 2 points. If you're doing this with a ruler, which I highly recommend, you're going to end up with something like, here's my line from here to there. Okay, take that away. Let's just make my point here. Take this guy, move it, move it. Where's my beauty? This guy. Put this here, put this here, tip to tail, put this here, and I move my original vector back that I drew. Look at that. They're like in the same exact spot. It didn't matter that I moved them. It didn't matter that I didn't with no ruler and freehand. It's always about the same. Okay, so hopefully that helps. We're going to do some practice when we get back together, but these are the basic rules that you should have in your notes. Why we need to do 2D vectors differently, the steps we take to sketch them, and finally how we can graphically and mathematically determine a resultant, or excuse me, just graphically determine a resultant. I hope that helps.